Hi everyone, I come from the Institute of Automation, Chinese Academy of Sciences, and I will introduce the applications based on SNAP2. As my colleague Shulin introduced in her report yesterday, SNAP2 is a powerful hardware platform with easy-to-use software. So what we can do with SNAP2? In the past few years, we have designed a back-end product, BTA128, specifically for telescope array, and one back-end product, BST8, specifically for single telescope. And we are trying to apply SNAP2 for other applications. The main contents of my report are these three parts. Backend for telescope array. BTA128 is a low-cost multi-channel digital backend. You know the budget is always inadequate, so the low cost is very important. This backend is mainly used for correlation and beamforming processing of large distributed radio telescope array. Its main features: sample rate 12 bits at 5 SPS, and the maximum input is 128, and it has various input and output interfaces. Obviously, the backend follows the general purpose architecture of CASPER. The F engine mainly completes the channelization, including time delay, PFB, FFT, phase compensation, quantization, and the X engine primarily implements correlation, beamforming, and accumulation. And the switch is responsible for the data transmission and exchange between the F engine and the X engine. And we use our own designed serial RepNet switch and 10 gigabit Ethernet switch. Application 1. The backend is the backend BTA128 is originally designed for the 21 centimeter array. The 21 CMA is a low frequency radio interferometer built in the remote mountain in the northwest province of China. The antenna array includes 81 poles distributed in the north-south and the east-west baselines respectively. And each port is an assembly of 127 antennas. The backend is placed in a simple sampling station room near the pod, responsible for the beamforming of 127 channels and transmitting the results back to the central computer room by the optical fibers. And the central computer room also provides the reference clock and the trigger signal for each station by the fibers. Its main features: 508 antennas, 127 antennas per port, sample rate 12 bits at 5 SPS, and the FFT channels is 40 points. 16 contact 7 boards are used for ADC sampling, and each of the 2 boards is cascaded to achieve the beamforming of 16 channels. And one SNAP2 is used to add all the data streams to get the final beam data. One of the major challenges of this project is how to achieve synchronous sampling. Here are some methods we used. Firstly, we select ADC chip with a synchronization function. And secondly, equal length design of hardware circuit, especially for data and clock. Thirdly, timing adjustment for data and clock using eye delay in FPGA. Transmission of reference clock to distributed sampling station by optical fibers, realizing clock homology. And lastly, synchronize the configuration, reset, trigger, and data upload between boards by using multifunction POSIs. Look at this picture. We choose one 10x7 board as the master, and the rest as the sleeves. And the master will send many multifunction POSIs to the sleeve and itself, which are used to synchronize the operations of all the boards. Finally, the 508 channels are synchronized after each power on. And if we provide a signal source as an input for all the channels, then we can see that the waveforms sampled by all the ADCs can be aligned in the display software. Here are some pictures of this project. This is the simple sampling station. Yeah, it's really too simple. So, the bad environment is also another challenge. However, the biggest challenge of this project is to connect nearly 800 cables of the whole system. If you do this work without patience, it will be a disaster. My painful memories. The second application of this backend is ultra-long wave telescope array prototype. This project is similar to the 21CMA project. The main difference of this project is the X engine performed beamforming and correlation simultaneously. And the blinking LED is a necessary part of the FPGA program. So we put so many LEDs on the panel to show the status of the backend. Its main features: 36 antennas, dual polarization, and the sample rate 12 bits at 160 max SPS, and the FSD channels, 2 key points. Yeah, it's architecture, the design file, and the display and the control software. The third application of this backend is mean unto spectral radio heligraph. Its main features 20 antennas, dual polarization, so 40 input channels. If intermediate frequency bandwidth 50 to 450 megahertz. The sample rate 10 bits at 1 gig FPS. 14 Snap2 boards are used for this backend. 6 boards are for the F engine and 8 boards for the X engine. An 8-channel prototype for MUSER has been delivered for use. And this is the correlation test. This is the linearity test. Okay, the backend for single telescope. BST-8 is is a low-cost digital backend with powerful processing capability and rich interfaces for the single telescope. You can see it has a variety of interfaces: the sampling clock, the sensing and the trigger signal, the reference clock, 8 analog inputs, 2 FMC ADC cards, out-to link, and 1 PPIs, IJ45 connector for the Ethernet, QSFP Plus for 10 or 40 gigabit Ethernet, LED, and out to QUFPG for the GPS timestamp. Its sample rate can be 10 bits at 5 gig FPS or 12 bits at 3.2 gig FPS. It depends on which ADC cards you choose. The SNAP2 can be connected to HPC to form a hybrid computing system. There are 2 ways to connect SNAP2 to HPC, by the 10 or 40 gigabit Ethernet or by the PCIe. This is the PCIe rising card, and this is the PCIe cable, and this is the SNAP2 board with the PCIe rear board. This backend has been used for the FAST project. It has 2 work modes, the spectral line modes and the Pulsar search modes. For spectral line modes, under high bandwidth mode, the max bandwidth is 2 gigahertz, and under the narrow bandwidth mode, the channel bandwidth can be less than 0.5 gigahertz. For the Pulsar search mode, it can work as incoherent mode, coherent dispersion mode, and baseband raw data storage mode. SNAP2 can also be used as a broadband spectrometer. 2 pieces of 3 gigahertz ADCs can be, by interleaving 2 pieces of 3 gigahertz ADCs, the 6 gigahertz sampling rate can be achieved. At last, we are now trying to use SNAP2 for the acceleration of dedicated computing. For example, the artificial intelligence inference, the database and the big data analytics, and the video transcoding, and so on. And a new version of SNAP2 with about 256 DDR4 memory is being designed. This is a prototype. The FPGA arrays can be plugged into the backplane with PCIe switch, and the backplane can be connected with the HPC by the PCIe cable. That's all. Thank you.
Okay, we have time for a couple of questions. Is the SNAP2 board and the ADC boards available for purchase? Or how is the production of those? The answer is yes. You spoke to them. So do you have any Pulsar data? I mean, so are these actually been deployed now? So you have Pulsar timing spectra and examples of your Pulsar?
The backend had been given to the National Astronomical Observatory of China. So we reuse it. We don't know the the result.
Lynn, do you want to add something to the first question?
Yeah.
No, I meant about can people buy the board?
Yeah, of course.
Yes.
Yes.
Did you say you both own 10 switch?
Serial replica switch. Yes, we have.
Is it easy?
In your first, maybe it was their first or second slide, it said 10 GD and then there were 4 other letters. SRIO.
Yes.
What does that mean?
Serial rapid I/O.
Okay.
What was the Kintex soundboard you used? You said you had an inexpensive Kintex soundboard that you used for some of the things. What board is it? Which board is it? Oh, the board that does this. No, it's one of those. Oh, it's their own board. Okay. Is it CASPER? Okay. Cool.
Any questions for Liangtian?
Okay, thanks.